Our first speaker today is virtual. His name is Professor Behcet Acikmese from University of Washington. His talk today is Optimization-Based Control and Aerospace Perspective. Welcome, Professor.
Thank you. Thanks for the invitation. I'm really happy to be here. This will be a brief talk. I gave a talk a while ago in KAUST, and this will summarize some of the research we have been doing in optimization-based control with an aerospace perspective. Here I will motivate. These are my standard motivations, but they are not getting old. There are many applications where optimization-based control can be highly effective. One of them is a mission to Mars. Actually, there are two of them recently. One is landed on Mars in 2012 and the other in 2020. I developed an algorithm that were used in both, that were used during the landing, and they both use optimization-based control. Another one is a development we have been involved in early 2010s and up to 2014. This was the first time where a vehicle, a rocket, was guided by an onboard optimizer and a trajectory planner. This was a test flight. It's called GFOLD, Guidance for Fuel Optimal Large Diverge. This was first successful use of optimization-based trajectory planning on board a reusable rocket. And these technologies have been used recently, not that recent anymore, approximately 5 years ago, by SpaceX, and they have been still in use for their reusable rockets, Falcon 9s. And we have been planning about other applications of these methodologies for future missions, for space and also aerospace in general. Here, first, I want to get my lingo straight, I guess. When I talk about trajectory planning, I mean generating trajectories, nominal trajectories, to be followed by a feedback controller to guide a plant or system or a spacecraft or aircraft in this case. And I'll focus on trajectory planning results in this presentation. We also work quite a bit on feedback control and state estimation, but I'll not talk about it much here. Our main approach is formulating the problems at hand as convex optimization problems. That's at the core of what we do. And here I want to describe what convexity is and what convex optimization is. In general, optimization is a branch of mathematics where you have a cost function, which is typically non-convex, meaning it may have multiple minima, that you are optimizing over a set of feasible solutions. This is the set. And the set may be non-convex too, meaning that there may be lines between 2 points in the set that go out of the set. Typically, when you have this kind of what we call non-convex optimization problems, it's hard to guarantee solutions in an automated fashion, especially if you want to solve them in real time. The approach we have been adapting is convexification, meaning a conversion of these problems into either equivalent or approximate convex optimization problems. In convex optimization, you have convex costs, which are much nicer. The cost functions are much nicer. They typically have a unique minima. And you optimize the problem over a convex set. If you can do that, there are highly reliable algorithms which are fast, then they guarantee also optimality. So they are potentially implementable in real time on board vehicles during operations. The main theoretical contribution has been convexification, meaning the conversion of problems on the left, which are non-convex, into convex problems in the realm of trajectory optimization or trajectory planning for autonomous vehicles. What's the trajectory planning problem? It has several components. The first one is dynamics of the vehicle you have to pay attention to. There are state and control constraints. Some are physical constraints that you cannot violate. Some are mission constraints that are desirable to satisfy. And then there are costs and rewards. These are things you optimize for, and they depend on the mission at hand. And the convexification, there are two typical methodologies we use. One is what we call lossless convexification. This is typically achievable when you have non-convexities in control constraints, in your control variables. And if you have other sources of non-convexity, we use sequential convex programming methods. When you have lossless convexification, you can convert a non-convex optimal trajectory planning problem with non-convex control constraints into equivalent convex ones. But when that's not the case, sequential convex programming allows you to generate a sequence of convex optimization problems which you can solve to achieve the solution of the original problem. In this case, we cannot call it lossless because we cannot fully convexify the problem. And typically we obtain locally optimal solutions, whereas in the first case, we can obtain globally optimal solutions. Nevertheless, we have significant progress in CP or sequential convex programming based methods that we are also deploying them in real-time applications. Here is an example, my standard example that I give for lossless convexification of a control constraint. This is a landing problem for a rocket, which is here simply modeled as a lump mass with a thruster attached to it. And the thrust vector has a magnitude upper bound. So you cannot have thrust more than a specified value. This is the physical limit. Another lower bound in magnitude, which is due to the fact that you cannot bring the thrust levels below a certain point because otherwise this type of thrusters become unreliable. They may shut down. So this itself generates this circular annulus that is a non-convex region. On top of it, you may not want to rotate this thrust vector too much relative to the local vertical. And this is because maybe there is a camera looking down, and rotating the thrust vector implies rotating the vehicle, and the camera may lose contact with the ground and so on. This generates this blue area, which is non-convex. We have been generating methods, mathematical methods that ensure lossless convexification of it. And here is another problem of this type, which is the quadrotor flight. And in quadrotor, you can model the quadrotor as a lump mass with a thrust attached to it. Thrust is due to the propellers, of course. In this case, also, there is an upper bound and lower bound. The lower bound comes from an interesting fact. Because due to the propellers, you may lose attitude control if you bring this thrust below a certain level. And also there may be pointing constraints on the thruster, again, due to maybe a camera looking down or a payload you are carrying and so on. Again, this is a non-convex region for thrust vector, which is the control input. And we developed these relaxations which take the original non-convex control constraints, relax them into higher dimension to a convex cone cut by a plane, and show that if we solve this, what we call lifted or relaxed problem, you can always obtain solutions. This is a convex problem, global optimal solutions, which also can be projected back into the original space to find the global optimal solutions of the original problem. That's why we call it lossless convexification. But as I said, this is only possible when you have non-convex control constraints. In the other case, in the general case, when you have mixed control state constraints that can be non-convex or pure state constraints that are non-convex, we use sequential convex programming methods to solve these trajectory planning problems, or in general, more mathematically optimal control problems. Here, again, you may have a cost dynamics of the system represented by this differential equation, state and control constraints, mixed state and control inequality constraints, some boundary conditions and such, which may be equality or inequality constraints. And we recently actually wrote a very extensive control system magazine article. Here you will find the link to archive publication, our archive version. The actual version will appear in Control System magazine of IEEE soon. And here is the link and so on. I'll send my slides, so if you want to check it out, you can reach to it, or you can go to my website or Google Scholar site. You can reach to this publication. It's very extensive. It has a link to our Julia Toolbox, which you can use if you want and get into sequential convex programming methods. The idea in sequential convex programming is following. There are several sources of non-convexities. One is nonlinear dynamics of the vehicle. They define nonlinear equality constraints, if you like, which define non-convex regions, feasible regions. And there may be other sources of non-convexity due to other constraints. What we do is we generate a sequence of convex optimization problems. The way we do that is we have an initial guess to the solution, which doesn't have to be an accurate guess, which can be actually quite off from an accurate or feasible solution. You start with it, you linearize the dynamics around it, generate a linear time varying dynamics. You convexify constraints by using this reference solution. By doing that, you generate a convex what we call a convex subproblem. You solve this convex subproblem with a convex solver, obtain the next trajectory, do the same iteratively at the trajectory level, and you keep on going like that. This process is typically convergent, and you reach to a local optimal solution, if there exists, of course, a feasible solution to the problem. And it's always convergent. If it is not a feasible problem, you will also get some hints about why it's not feasible. And we have been using this type of methods with some variations over many problems. The difference of this method with the more classical methods of optimal control is that in the classical, more standard methods, people discretize the problem in a nonlinear, non-convex fashion, and so send the problem to a non-convex solver, like a IPOpt, which is well-known non-convex optimizer. Instead, we are, and then that solver itself does the convexification internally, if you like, locally, and then it uses some sort of sequential convex programming techniques. We do this step of convexification in the problem, in the trajectory planning problem level, and use a solver, convex solver. So when we send the problem to a solver, we always send a convex problem. That way we actually know more about what's going on with the subproblem we send to the solver. We have more control over this sequential way of generating trajectories and so on. And this gives us some theoretical advantages as well. As I said, there are some examples in this toolbox that we put out. Here is one example relevant to current applications. This is the simple model, relatively simplified model of SpaceX Starship. Of course, we made up some of the parameters, like mass and other inertia and so on. We don't have access to those, of course, but this is a relatively nice toy. But it's still an applicable problem you can find with many interesting constraints. And as I said, the Julia package uses, in the version we put out, the ECOS, which is a publicly available second-order programming solver. We have been putting this out, and people have been using this solver. I encourage you to use it too. And here is the link to the solver. I will send it to the organizers so that you can have access to. It's developed originally by my student Danilo Magliuta, and others contributed to that package too. Some of my students are Purna, Sky. I want to name some here. And we gave also a sequential convex programming toolbox workshop in a recent aerospace conference in Breckenridge. And there is a tutorials repository. Again, I have links here if you want to use this package. The code runs out of the box, so you don't have to hopefully do too much. And there are some toy problems. Another toy, not really toy, actually, they are quite realistic problems. One is this planetary landing trajectory planning problem you can play with. And I want to, maybe in the last 5 minutes, I want to talk about some of the, a key component of solving these problems reliably in real time is having a convex optimization algorithm, a numerical algorithm to solve this convex sub problems that we generate in SCPs. For that, we have been developing first-order methods for conic optimization, which is customized for trajectory planning. Conic optimization of this type, where you are minimizing a quadratic cost defined with a positive semi-definite matrix P. There are some conic constraints and some convex constraints. We differentiate between those for where K is a convex cone. By the way, this convex cone just can be zero, meaning HC may be equal to zero, a linear equality constraint, for example. And this convex set D is a set that you can easily project. That's the idea. The key point is that it's easily projectable in closed form set, all right? And a lot of linear programming, second-order comp programming, and semi-definite programming problems are examples of this type. And we propose a proportional integral projective gradient algorithm, which is a first order method to solve this problem. And it is a very simple algorithm, actually. It has a linear update rule, which is a gradient descent rule, if you like, and a projection operator. That's the only thing you have to do that's complex. And our assumption is this projection onto this set is D is simple. And for most trajectory planning problems, it's simple, actually, because trajectory planning problem constraints are typically decoupled in time, and you only have to project each state variable at a given time onto this on a set that's typically low dimensional. And there is another step, which is it's almost like an integrator in the PI. If you study PI control in control theory, this looks like an integrator. And then there is another projection onto the dual of the or polar cone of the K, the cone K that defines the problem. And this algorithm is, again, quite straightforward to implement and also quite straightforward to verify and debug, which is also very important when you want to push this type of algorithms to real applications. That's why I like this. This is recent work, and I'm hoping that this will grow further. And this algorithm doesn't require any matrix computations, that is more than matrix vector multiplications, no Cholesky decomposition or any other form of decomposition. You can exploit the problem structure very effectively. And as I said, simple algorithm and code easy for verification. And simple projections can easily be done onto balls, boxes, cones, and half spaces. That's what we take advantage of. Projection is basically Euclidean projection, which is finding the closest point in the set to a given set. That's what I mean by projection. And these are some theoretical guarantees for the algorithm. It has very strong convergence results to optimal, and also we have also results on how fast we recover feasibility and so on. Again, I will not talk about this, but it has strong theoretical guarantees and strong practical implication that these algorithms work very fast. Here is a simple example of forward motion planning around obstacles, and we compare our algorithm, which is PIPG, to other algorithms like ADMM, primal dual hybrid gradient method that's proposed recently, and our algorithm seems to do very, very well in terms of convergence rate, both for convergence to optimal solution and reducing the constraint violation as the iterations go on. The difference between this kind of first order algorithms and second order algorithms like IPMs, interior point method algorithms, is that typically these algorithms take more iterations than IPMs, but per iteration, the complexity is much, much, much less. That's how you gain in terms of computation time at the end. And another application of this type of algorithms is, that was my core application actually initially, Mars pinpoint landing, where you want to bring a lander vehicle to 100 meters of a target. Till now, our requirements were always in kilometers in the last 2 missions to Mars. And we developed the lossless convexification-based algorithms and demonstrated, as I said, with a test rocket. This algorithm was called G-fold. Here are some test campaigns, flights, rocket flights. I put the links in these flights here in my presentation. I don't have time to show them, but if you are interested, you can either go to my website or I'll send the slides later. Again, SpaceX landings for Falcon 9 are amazing examples of use of convex optimization in flight. And Dr. Lars Blackmore was the key developer of this in SpaceX. He's their key chief guidance, navigation, and control engineer, my close collaborator. And I'm currently working with also a team of NASA scientists to develop next generation moon landing, planetary landing in general algorithms. This project is called SPLICE. That's something that I'm working on actively. And here are my past group members who contributed to my work here. There are many of them. I'm really indebted for their hard work. These are our sponsors. I'm thankful to them to make this happen. And thank you for listening to me. If you have questions, I'm more than happy to answer. I think I finished it in 19 or 18 minutes. So we have some time. Thank you.
Thank you, Professor, for your talk. I'd like to ask if there are any questions. We'll bring the mic to you. While we're waiting for questions, I have a couple of my own. First, how long was it from the time you and your collaborators came up with algorithms for, say, the pinpoint landing on Mars or the SpaceX landing to the time that it was actually implemented on these spacecraft or aircraft?
That's a very good question. For example, lossless convexification algorithm that I come up for Mars landing, I think I came up with it towards the end of 2004. Of course, developing the actual solvers and all these things took some time, but eventually the flight tests, first ones happened in 2011, I believe. Yeah, it was 2011. First experimental flights on a test rocket. Then, of course, aerospace industry is a bit conservative to push these things. It's not easy. First, actually, this algorithm was used by systems engineers. It's an interesting story. I developed this algorithm. The reason was the system engineers wanted to run Monte Carlo analysis. And in Monte Carlo, you are running a bunch of scenarios on a computer. And the bottleneck that they were running into is that they were using a nonlinear solver, nonlinear programming solver, which was producing infeasible solutions even when there existed solutions. So some of their simulations were turning into garbage. And for each trajectory, it was taking maybe, like at the time, at least a couple of minutes to solve the trajectory, or even more sometimes. So it wasn't very good for simulation. They would give a run overnight. The next morning, like 20-30% of the result is junk, and the other took a lot of time. When I give them this solver, even the earlier versions, which were not optimized in any way or form in MATLAB, solved the problem in 6, 7, 8 seconds, and it never failed unnecessarily. So they could run Monte Carlos much, much, much faster than they used to. They love this tool. Later on, my simulations got even faster. Eventually we were running this in milliseconds, reliably. So that really pushed the algorithm, because a lot of people used it without me being in the loop and my collaborators. And that gave a lot of confidence. Eventually that caused that test flight. Then my colleague who later on came and worked with me, Lash Blackmore, went to SpaceX. He found applications and this approach, a use for this type of approach in SpaceX. And they started using convex optimization. I think they had to prove that it also is useful and it will solve a problem that otherwise they couldn't solve with simple heuristics. I don't know all the details of his story, but eventually they found a reason to use it, and that was enabler for them during the landings of Falcon 9. And he has a very nice article in, again, it's in one of my references. You can go and read the story. It's more of an easy read. I would strongly recommend. He talks about a little bit of these details.
Thank you very much. Are there questions here from the audience?
Thank you, Professor, for the nice talk. So I'm wondering, when you build this algorithm, did you take any disturbance into account? And the second thing is, this algorithm looks like the MPC. Model predictive control. Can you say a few words with the difference between this algorithm and the MPC? Thank you.
Sure. In the planning, we didn't use any disturbance. We assumed deterministic propagation. Nowadays, I'm working with the disturbance included in the planning, but at the time, we didn't consider disturbance. What we did is we left some buffer in both control and state constraints, generated trajectories with that buffer, and that buffer was used for the feedback part of the problem, meaning that to track these trajectories, we also have a lower level feedback algorithm, control algorithm, which is a reactive algorithm ultimately, which ensures all the things that aerospace industry want to see, like gain phase margins and so on, And so that, with the feed forward and feedback, you can execute these trajectories reliably without violating constraints within these extra buffers that we put. In comparison to MPC, in MPC, you typically do receding horizon MPC, meaning that you slide your horizon and then you keep on solving the problem. Here, we didn't do that because, first of all, we don't have receding horizon problem. It's legitimately shrinking horizon problem. And the other reason is they didn't want us to solve in real time many times. There had to be a good reason to trigger a recomputation. And that good reason is typically if you deviate from your original trajectory too much, you know. And it didn't happen in any of the things because our feedback controllers were good enough. Actually, having said that, there was one instant in one of the test flights, the winds were much more than what we expected. And that caused a little bit of a headache. The performance of the rocket was a bit jiggly. And the reason was because we didn't, it went, the wind effects, which were disturbances for this case, went beyond what we expected. But again, with proper feedback, it could have been handled. Having said that, these algorithms, now I'm developing also algorithms which are more conscious of the disturbance models, and they can incorporate disturbance model into planning as well, not only handling them via feedback, but plan for them in advance. You know, we are working on that currently, if that makes sense.
Perfect. Thank you so much, Professor, for your time and for being with us today. Really enjoyed your talk.
You're welcome, and I'm very pleased to be here. And thanks for the organizers to invite me. And thanks to the KAUST community. Thank you.